One problem facing the designers of the next generation of turbojet engines is that of increasing turbine inlet temperatures. Air-cooled turbine blades may offer a solution to this problem. The fabrication of a cast air-cooled turbine blade that has shown promise in prototype testing will be shown in this film. This blade was made using a modification of the lost wax casting technique. A process to provide long, slender holes for cooling passages was developed by the Lewis Flight Propulsion Laboratory of the National Advisory Committee for Aeronautics. This development is particularly important because the superalloys used in aircraft turbine blades are extremely difficult to machine. Ceramic tubes are used as part of the casting mold to establish cores or holes through the turbine blade casting. Core tubes of the desired outside diameter are assembled in a pattern die. The core tubes are held in place by embedding them in a bar of soft wax using a hot wire or knife. The dies used are made of a low-melting alloy cast around a brass master pattern. A casting pattern is made by closing the dies containing the ceramic tubes, clamping the dies in a wax injection machine, and injecting molten wax under pressure. The wax pattern containing ceramic tubes is removed from the die and excess wax is trimmed, leaving a light wax film on the exposed ceramic tubes to permit freedom of movement due to expansion. Additional pieces of wax are assembled by welding with a hot wire. These pieces will form sprues, runners, and ingates or passages for the molten metal to reach the blade cavity in the casting mold. The assembled wax is mounted on a waxed base to seal it. A can-type flask is placed over the assembly, and it too is sealed at the bottom. When the investment is thoroughly mixed, it is poured into the flask and around the wax pattern assembly. The flask is then placed in a vacuum chamber to remove air from the mix. After investing and air drying, the molds are placed in a furnace. Here the drying is completed, the wax is melted out, the wax residue is burned off, and the mold is cured. During this furnace cycle, the temperature is gradually increased from room temperature to 1900 degrees Fahrenheit. Metal alloy for the casting is melted in an electric induction furnace. When the metal reaches a temperature of 3000 degrees Fahrenheit, the crucible of molten metal is placed in a centrifugal casting machine, and the hot mold is placed over it. As the casting machine is spun, the molten metal is thrown into the mold. The casting is removed by breaking away the mold. After the casting is cleaned up, the ceramic tubes used to form the cooling passages in the blade must be removed. This is done by threading fine stainless steel wires through each ceramic tube and stretching them taut on a frame. The turbine blade is then attached to a cam device designed to slide the blade up and down on the wires. The lower part of the assembly is then immersed in a bath of molten caustic. This helps to remove reaction products and introduces fresh caustic to the bore of the tubes, and hence accelerates the solution and removal of the core tubes. The rough casting is cleaned in an air-water abrasive blast. A suitable base configuration is then ground, and the blade is ready for testing in a research facility. The process you have just seen illustrates a principle that has been effective in producing long, thin-cored holes in castings. This process may be useful in fabricating turbine blades to be used at very high turbine inlet temperatures.